All right, friends, let's finish up lesson 312 today. We've got 6 examples. We're going to solve some equations using trig functions. This is Miss Adams from Flamingo Math. We want to find the solutions for the equation on the interval from 0 to 2 pi, and I'll let you verify with your graphing utility. In this first one, we've got the sine of x plus pi over 3. We can expand that using the sum of two angles formula, which is sine of x cosine of pi over 3 plus cosine of x times sine of pi over 3. And then the difference is going to be sine cosine minus cosine sine. And we want to see that that's equal to 1. So I see this cosine sine would subtract this cosine sine, and we would end up with 2 of the same terms. So 2 sine x cosine pi over 3 is equal to 1. And cosine of pi over 3 is a half. So the sine of x, I messed up my x here. 2 sine of x times the cosine of pi over 3, which is a half, is equal to 1. So what do we have? The 2 times a half is 1. Sine of x is 1. Where is the sine of 1 on the interval from 0 to pi over 2? That would happen, no, from 0 to 2 pi, I'm sorry. But the sine of x is 1 only at pi over 2. And you could verify that if you graphed this equation on your calculator. And this equation is equation 2. You should see an intersection at pi over 2. Let's look at the next example. We want to find the solutions on 0 to 2 pi and again verify it. Using our double angle formula, the sine of 2x is 2 sine x times cosine x plus cosine x is equal to 0. We can factor out a cosine of x and end up with 2 sine x plus 1. Solve the first factor. Where is cosine 0? That would be at pi over 2 and at 3 pi over 2. And then where is 2 sine of x plus 1, 0? That would happen where sine is negative 1/2. And there's 2 locations on our unit circle where sine's negative 1/2. That would be 7 pi over 6 and 11 pi over 6. So we have 4 possible angles that you would see an intersection, an x-intercept at pi over 2, 3 pi over 2, 7 pi over 6, and 11 pi over 6. For example 15, we want to solve where sine times cosine is a half. So thinking about something algebraic here, let's do sine times cosine is 1/2. We could multiply both the left and the right by 2. And this is my double angle formula. I see the sine of a double angle is equal to 1. Well, sine of x is 1, only at one place, right? Sine of x is 1 when x is pi over 2. So 2x is pi over 2 plus 2 pi n, and dividing by 2, x is pi over 4 plus pi n, and we want to stop at 2 pi. So we want all the angles between 0 and 2 pi. So that would happen when our n value is 0, one place would be pi over 4. When our n value here is 1, 1 1/4 is 5 pi over 4. And if our n value is 2, we're outside of our given domain. So only 2 places where sine times cosine is a half. Example 16, they're getting a little more difficult here. Cosine 2x plus 3 sine x minus 2. I want to use the identity for cosine 2x, this piece right here. We're going to say 1 minus 2 sine squared x. That came from our first page of notes on this lesson. Plus 3 sine x minus 2. And I used this particular formula because my middle term was in terms of sine. So adding up what we have, let's think of this as positive 2 sine squared x. So if you multiply through by negative 1, you can get that. So positive 2 sine squared x minus 3 sine x, and then 2 minus 1 is a positive 1. And you can factor those three terms as 2 sine x minus 1 times sine x minus 1 and solve for those two factors. Where is 2 sine x minus 1 equal to 0? That's going to happen where sine is 1/2, which is pi over 6 and 5 pi over 6. And then where is the sine of x minus 1, 0? That would happen where the sine of x is 1, and we said that's only at pi over 2. So we have 3 solutions for this particular equation. And again, I'm having you check on your graphing calculator just for saving time. Make sure those are accurate. We got 2 more to go. 17 gives us the sine minus the cosine is equal to 1. So we could do this. Where is sine? Let's think about this. Where is sine minus cosine equal to 1? So how about if we, let's see, how about if we squared both sides? What would happen if we squared both sides? We'd get sine squared minus 2 sine cosine plus cosine squared equals 1. And sine squared plus cosine squared, that's 1. And 1 minus 2 sine cosine is 1. Let's see, this is our double angle formula, so we've got subtracting 1 from both sides. We have the sine of 2x is equal to 0. So I'm thinking about this. If you multiply through by negative 1, these two negative 1s are gone, and we end up with the double angle identity. And we know that the sine of x is 0 when x is 0 or pi. And we know that we're going to have some extraneous solution because we've squared things. If you square both sides, x equals 0 plus 3 pi over 2, that's going to be extraneous. So the only thing that would work would be, let's think about this, when 2x is 0 plus 2 pi n, x is 0 plus pi n, and that's where that extraneous happens over here. And then 2x is pi from these two. So we got it 0 and we got it at pi, plus 2 pi n, dividing both sides by 2. We got pi over 2 plus pi n. So our only two answers are going to be at pi over 2, and pi. So we can't get the 0 here. We can't, and we can have pi, and we can have pi over 2 from here. Our last example is also a little tricky. We want to have sine of x minus radical 3 cosine equal to 1. So I'm going to introduce that squaring both sides again. The sine of x, let's add this to the 1, is 1 plus radical 3 cosine. So anytime we square both sides, we're going to end up having that. You got to check for extraneous, because we're introducing the possibility when we square both sides. Squaring the left, sine squared. Squaring the right is two binomials distributed out together. So we got 2 square roots of 3 cosine, and we have square root of 3 squared is 3 cosine squared. Let's see, we got 2 square roots of 3 and 3. So we got sine squared can be rewritten as 1 minus cosine squared. I'm rewriting this so that we have everything in terms of cosine. And then 1 plus 2 radical 3 cosine plus 3 cosine squared. The 1's are gone, 1 on this side and 1 on this side. If we add this 3 and this 1, we end up with 4 cosine squareds, adding this to the other side. And then we still have plus 2 square roots of 3 with a cosine. We can factor out a cosine. This is a lot of algebra. 4 cosine and 2 square roots of 3. Where is cosine 0? So cosine of x is 0 at pi over 2 and 3 pi over 2. So we're going to check those. And then this second factor, 4 cosine x plus 2 radical 3 is 0. When cosine, we're going to subtract 2 radical 3 and divide by 4. So where is cosine? Negative square root of 3 over 2. That happens at, let's see, not at pi over 6. We got 5 pi over 6. That's in quadrant 2. At 7 pi over 6. So we're going to check these. And what are we doing? We're going to go back to the original equation. This is our dilemma here. So if we go back to the original equation and you try pi over 2 here, we get the sine of pi over 2, which is 1, and the cosine of pi over 2 is 0. So 1 minus 0 is 1. Pi over 2 is a valid answer. So we have pi over 2 works. This does not work. And then we want to check 5 pi over 6. So think about the unit circle here. At 5 pi over 6, the cosine is negative and the sine is positive. So we have the sine of 5 pi over 6 is 1/2 minus square root of 3 times negative square root of 3. So this becomes a positive 3 over 2. A half plus 1 1/2 is 2. So this answer doesn't work. And 7 pi over 6 is down here. That's going to give us sine is negative a half. I believe that one's going to work. So 7 pi over 6. Because the sine, they're both negative. Square root of 3 over 2, negative a half. The sine is negative a half. And we've got minus radical 3 times negative 3 over 2, which is 3 over 2 minus 1 over 2. That's 2 over 2, which is 1. So that one works. We only have 2 solutions that work for this equation. Pi over 2 and 7 pi over 6. We had extraneous solutions because we squared both sides and had to check that those two were not valid. Boy, that was a tough lesson. We're done with lesson 12 in AP Pre-Calc.